Hey everybody, it's Liz. I'm back here for lab 2. And so this week we're going to be doing population estimation using the Peterson method of population estimation. And so we're going to be working with the same data set that we worked with last time, the Tallgrass Prairie National Preserve data. So why don't you go ahead and if you haven't already, open up RStudio, download your code, and then go ahead and also open up the Word document for lab 2 that you see I have in front of me right now. And so today we're going to be going through population estimation. And so we're going to be talking first about the Peterson method. And so the Peterson method of population estimation for fisheries management uses the formula N equals MC divided by R, where N is the population size at the time of marking, M represents the number of fish marked, and C is the total number of fish in the second sample. And then R is the number of recaptures, so the number of marked fish in a sample, and the sample is C. So for example, if we use the pivot table function in Excel, we can obtain M, C, and R values for each pond on the Tallgrass Preserve, and then we can calculate N and for each pond using R. So go ahead and take a moment and open up your Excel spreadsheet and fill in those values before you continue. So next up, we're going to be talking once again, we touched on last lab a little bit about confidence intervals and standard error. So the standard error of the mean can be calculated using the following formula, where standard error equals the square root of m squared times c minus r all over r squared. And so one simple method for obtaining these confidence intervals is provided by the formula in line 36. And so we have 95% confidence intervals for N would be plus or minus 1.96 your standard error. And then 80% confidence intervals would be plus or minus 1.28 standard errors. And those values you're going to extrapolate from a table, right, of your values based on whatever your alpha is going to be set at. And then remember that in order to calculate an interval, you always do upper minus lower. Okay, so we're going to start opening up some code and look at the R code provided and calculate the standard error for our largemouth bass population estimate. And we're going to do it separately for R. And so you'll put those values in here when you go through R. And then your assignment for the week is also going to include manipulating the R code on line 36 and calculate both the 95% and 80% and the intervals separately. And then I want you to make a bar graph with 5 population estimates and their 95% confidence intervals with axis labels and an informative figure caption. And you can insert your figure in the space below. And we provide the code for you. All right, so let's go over here to our RStudio and start cruising. So I'm going to set my working directory again. But first we should go through and read just a little bit of all of this information. So estimates of initial population size along with associated confidence intervals are constructed from a single or multiple census mark recapture data using a variety of methods. For single census data, the initial population size, or N, is estimated from the number of marked animals from the first sample, M. The number of captured animals in a second sample, little n, or R in our data sheet, big R, as well as the number, the number of recaptured marked animals in the second sample, so little m, using the naive Peterson method. You can also use the Chapman and Ricker methods or the Bailey modifications of the Peterson method. The single census data can also be separated out by group, in this case size class, to estimate the initial population size by class for the overall population size. For multiple census data, the initial population size is estimated as the number of captured animals, the number of recaptured marked animals, M, and the number of marked animals that are marked and returned to the population, so R, the recaptures, or the number of extant marked animals prior to the sample, capital M, on each of several samples using either a Schnabel or the Schumacher-Eschenmayer method. This is all long-winded stuff, and the little introductory material in the Word document makes way more sense. Okay, so we're going to go ahead and read in our pond data with the pond pop estimates data. We're going to go ahead and view the data set and plug in the appropriate values into the code below. So there's pond data. we're going to load the Fisheries Stock Assessment, or FSA, library in R. So you might need to add it to your R library if you don't already have it. It's kind of an older library. It needs to be updated. Okay, so now we're going to go ahead and do the Peterson method. So we've gone ahead and calculated the N and then the standard error and 95% confidence intervals for the first pond for you. So now you're going to need to copy and paste and do this for the other ponds. Okay, so the first method, we're pulling all of these out for Gashouse North. And then we're going to do a summary. And then based on this value, we see that the standard error was 143.1. So we're taking that value times 1.96 to get the 95% confidence interval like we saw above. Bingo. Okay, so now we're going to calculate the lower confidence interval, upper and lower. So we can use this confint function, confint, in order to calculate the confidence intervals. And now we have 95% lower is 403, upper is 1008 is our population size. So up to 1,008 fish that were within 95% confidence. Okay, and to explain confidence intervals for a little bit, so that suggests that we are 95% confident that whatever the population is, it is between 403 and 1,008. So that means that there's only a 5% chance that it is outside of that range. Okay, cool. So next we're going to do the Gashouse South LMB estimate. Same song and dance using the standard error. And so now you guys have that code and you can go ahead and manipulate it. And basically we will copy and paste it. And you just do that for each of the other impoundments. Okay. Next up, we're going to create a vector containing the 6 new pond data for 2018. And we'll do the pop estimates in order and concatenate them to the data set. And so in order to do that, you're going to enter the N values you calculated above in order, separated out by commas. And so this is where you would put those in separated by commas. You would attach them, create a data frame, run it in ggplot. All right, so next up, we're going to need code that we'll use to create a bar graph with 95% confidence intervals. And so this ggplot2 is a really great library. It's a pretty simple but beautiful way to create complex figures. And it's really malleable for everything that you use it for data visualization. So we've got ggplot, and first is our data frame, and then AES, we're putting in what our X and our Y variables are. We're telling it to make a bar plot. The stats will be the identity. Then we're going to do a geom error bar. So we're telling it we want confidence intervals. We're telling it how wide they need to be and what theme, like what style the graph should be. All right, now we're going to talk about the Schnabel method. So you guys should go ahead, by the way, and experiment with those ggplots to figure out what they look like. Okay, so now we're going to use the Schnabel method on the Poudre River data set. So go ahead and read in the Poudre River data set, read in the library, and then we're going to subset the first, the second, and then the third, and then the first 4 sampling periods. And so we're calculating these abundance estimates from repeated mark recapture experiments following Krebs et al. 1989, which is a really useful text on mark recaptures. But here is a line of code where we're gonna run a Schnabel on the catch, and that gives us our N value, so our sample size. It gives us our lower and our upper confidence intervals. Now we're going to use the Leslie method using Creek Chub data set, the Creek Chub data from Kings Creek. So we're going to read in this Chub file, attach it, do a Leslie. So it's telling us our estimates are suspect as the model did not significantly show a negative slope. So we're creating a vector of the output from the Leslie output of K, creating a vector of CPUE, concatenating that vector of CPUEs to the Chub data set, making Chub a new data frame, attaching those variables so we can call them in by name. Then we're going to plot We're going to plot these. Figure margins too large. Cool. Let's try that. Cool. All right. So I just changed the PCH to make it a little bit smaller. Here we go. Yay. So you can just change the different styles. Okay, and then this AB line right here gives you a regression line. And then here's a simple linear regression, so we can get the R squared value, the slope, and the intercept. And so we've got our model. So we're calling in our model of CPUE by K value, and then our summary. And so here we have the output again with our multiple R squared, our adjusted R squared on 3 degrees of freedom, the F statistic, and the P value of 0.1572. So at the alpha 0.05 confidence level, is this significant? The answer is no. The relationship is not significant at the 0.05 alpha. So depending on what you set your alpha level at, could be. All right, so that was lab 2. Now we're going to go back over to this Word document and talk about some of the assumptions. That we have. Okay, so these are assumptions that have to be met for our population estimate to be valid. And so I want you guys to think about whether or not these are valid for what we did out at the Tallgrass Preserve. So first, we assume that natural mortality and emigration are the same for marked and unmarked fish. So both fish that get tagged or clipped and fish that don't have the same amount of natural mortality, and they are moving in and out of the population at the same rate. We assume that there's no loss of marks, that tags don't fall off or clip marks don't heal. We assume that there's a complete recognition and reporting of marks. We assume that there's an equal chance of catching marked and unmarked fish. We assume that the marked fish are mixed in randomly with unmarked fish. So when we're pulling out of a bag, we're not pulling out like 10 out of 100 of the marked fish. We're not pulling out all 10 of them in a row, because that would suggest that we didn't scramble our fish in a bag that well. To use that example. And then finally, we assume that there's no recruitment in between the marking and then the recovery, or like when you recapture them. And then also just this relationship of M times C is always greater than 4N. And if it doesn't meet that assumption, then that's not valid. All right, I need a drink here. I'm cruising. Okay, so now the Schnabel method. So the Schnabel method is a multiple method. So fish are marked and recaptured several times within the same population. So it happens multiple times. So the population estimate is obtained using the following equation. N equals the sum of CT times MT divided by the sum of R. So M sub T is the total marked fish at large at a given time. So all the marks. CT is the total sample collected at a given time. And then R is the number of recaptures in that CT sample. All right, so here's another example where we've got this data from the Poudre River data set, and we went through that already. And so we did the marking and the capturing, and I want you guys to go ahead and use the R file to calculate those population estimates for each of those values. And then once you've finished those calculations, fill in the blanks in the table below. And again, the assumptions are that the errors due to recruitment, natural mortality, and fishing mortality tend to be the most important. Thus, the best population estimate can be obtained by shortening. So we reduce the amount of time in which the estimate is made. So we reduce the time between marking and recapture. If we do it within a span of time, like a couple weeks, a few days, a few hours, the shorter the window, the less likely, or the more likely that you're going to get an accurate estimate, because the less likely fish or birds or whatever your sample is are going to be able to leave during that short time window. Does that make sense? Hopefully that makes sense. Drop a comment below. Click like, subscribe. Let me know how you think I'm doing and what I can do to improve. I am just out here to try to spread my basic, simplistic fisheries management knowledge with the masses. So if these videos have helped whatsoever in helping you learn about some of these basic fisheries data analysis techniques, let me know. Love to hear from you. All right, next up, we're going to use the Leslie method. So this is a cool population estimation method because it doesn't require you to mark fish, so much less work is involved. So it's applicable when a population is fished or sampled enough to reduce catch per unit effort, which is considered proportional to stock density or the population density present. So this method is often used where commercial fishing occurs because we know that as we sample or fish with commercial fishing, we are reducing catch per unit effort, right? We're taking fish out of the system. We're not just marking them and throwing them back in. So for our purposes, it's especially useful for population estimation in small waters or blocked stretches of streams. So for my dissertation research, I work in small Kansas impoundments, so small reservoirs less than 300 acres, surface acres. And so in these small waters, using the Leslie method is great because it doesn't require us to mark fish. And so the assumption with this method is that with enough effort, all fish could be eventually removed from the sampling site. So it's depletion sampling. And so this assumption is described in the following paragraph. Okay, so for this exercise, the following graph. So this exercise comes from a depletion survey of creek chub conducted in Kings Creek in 2012. So here we've got our 5 sampling events. We've got our catch of chub. These are the effort. And so in our case, that's the shocking time in seconds. So this is 220 seconds. This would be 196 seconds. CPUE is the catch, this divided by that. So catch per unit effort, 4 divided by 220, and so on. And then K is the cumulative catch. So that's calculated by summing all fish collected in the previous samples plus 1/2 collected in the current sample. So that would be 220 plus 1/2 of 241. Does that make sense? That would be the K value in here. So we calculate the CPUE and the K value using Excel. And I want you to copy your values of CPUE and K into the above table, or just calculate them on a piece of paper and put them in there. And then we're going to use the R code that we already did to create a scatter plot with K and CPUE. And so you don't have to include the scatter plot in your report, but you are going to need to give me the slope, the y-intercept, and your population estimation. And that is all for Lab 2. I hope this video helped. Thanks for watching.